Okay, in this video we are going to show an example that shows how to create a probability distribution for a binomial distribution. So we have this binomial probability function. I'm going to show you where this formula comes from. So remember, the probability function is going to give us, right, the probabilities for given values of a random variable x. And then we can learn in another video how to create the expected value and variance for the binomial distribution. So I'm going to show you how to do this. So let's just start with an example. So let's say 3 people enter a store. The probability that they purchase something is 0.3, like 30%. What is the probability that 2 of the 3 make a purchase? Okay, so up ahead of time, I'm going to tell you that the answer is 0.189. So we're going to go through an example and hopefully come out with this answer. So again, 3 people enter a store. The probability that they make a purchase is 30%. What is the probability that 2 of the 3 make a purchase? Okay, so one, is this a binomial experiment? Because if it is, we can use that binomial probability function to calculate our probabilities and then to answer our question. So here are the properties, and here is the support that it is a binomial experiment, right? It consists of a sequence of n identical trials, right? That's true, right? There's 3 of them. 1 trial for each of the 3 customers who enter the store. There's 2 outcomes that are possible, right? People either make a purchase or they don't. The probability of a success is denoted by P, right? So that's, does someone make a purchase, right? The probability is 0.3. And then failure is 1 minus P, so 1 minus 0.3 is 0.7. That's that they do not make a purchase. And remember, this does not change from trial to trial, so we're going to assume that this is the same case for each trial and for each person. And then the purchase decision of each customer is independent of the decisions of the other customers, right? That means the trials are independent. So basically what this is saying is that if someone comes into the store, right, the chance that they make a purchase is 30%. Right, this is true of every customer who comes into the store, and then each person who comes into the store, their decision to make a purchase is independent of other people. We're going to make that assumption. You might argue otherwise. You might say that, hey, you know, someone came in with the intention of purchasing something, whereas someone else came in, you know, and they were just browsing. You could say that, hey, what if 3 people come into the store and they're all related? They all came in to buy the same thing, the same shirt for a contest or something. You can make that argument, but remember, a lot of statistics is based off of assumptions, so we're going to make these. There's actually a different way that you can actually calculate probabilities when these assumptions are violated. We're not going to talk about it, but it's always good to check your assumptions, because if any of your assumptions are not met, then that jeopardizes the conclusions that you come to. But let's just make the assumption that this is the properties have been met. So let's continue. So let's first think about, okay, well, how many possible combinations are there for the outcome? So remember, the outcome we're interested in is that 2 people of the 3 make a purchase. So let's see here on the left, the first customer comes in, they even make a purchase, right, success, or they don't. The second person comes in, they make a purchase, or they don't. The third person comes in, right, they make a purchase or they don't. So we could have purchase, 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 right? That's the first outcome, right? In this case, everyone, all 3 people would make a purchase. The second would be purchase, purchase, no purchase, right? Purchase, purchase, no purchase. That's 2 people, right? And we can continue looking at all these different lines. And so these would be all of the different outcomes. And then here's the different values of x. So we have one case out of 1, 2, 3, 4, 5, 6, 7, 8, where all 3 people make a purchase. We have, in the case of what we're interested in, 2 people making a purchase. We have 1, 2, 3 situations. So this is important. Really, out of the 8 different possible combinations, right, there are 3, right, 1, 2, 3, that meet what we're interested in. Because if we go back, remember, we're interested in the probability that 2 of the 3 make a purchase, right? So here we got purchase, 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 purchase. So there's 3. So remember, when we're thinking about combinations, we already learned about from a previous chapter combinations. So if you remember, this is the old, actually earlier in this chapter, sorry, I'm getting my chapters confused, an earlier equation where we learned about the number of outcomes providing exactly X successes in N trials. So we already know we have 3 trials, and we're looking for 2 successes, right? 2 purchases. So we can use this equation, right, and substitute X, right, for 3 and N, or excuse me, 2, and then N equals 3. So that's what we did here to figure out the possible combinations. So we got N is 3, X is 2. We plug in all the values. We do the math. Remember, 3 factorial equals 3 times 2 times 1. And then it comes out to be 3. So that totally makes sense with what we just counted, right? There are 3 possible combinations where out of the 3, 2 are successes. Okay, so so far we figured out how many possible combinations are there. We've learned that there's 3. So now we have to figure out, well, what is the probability of any of these combinations happening? So remember, the trials are independent. And we learned from chapter 4, the probability of independent trials can be determined using the multiplicative law. I think we call it the multiplication law. So that's just multiplying your probabilities together. So that's exactly what we're going to do. So there's 3 trials, so we're going to multiply actually 3 things together, and 2 of them were successes. So we're going to multiply those probabilities together. So probability 1 is a probability of success, which is, right, 0.3 purchase. The second one, right, is again a probability as a success, as we have 2 successes. That's P, that's 30% again, 0.3. And then the last trial, right, is not a success, it's a failure. So failure equals 1 minus P, so that's 1 minus 0.3 is equal to 0.7. So if we multiply these 3 numbers together, right, these independent trials, the probabilities of each of them, if we multiply them together, right, we get 0.063. So this is the probability of the combination. So there's actually a shortcut, an equation for that. So the probability of a particular sequence of trials is equal to P raised to X, right? So if we actually look at here, here's this equation written out. So P, right, of X is a success. We're interested in 2 successes. The probability of success is 0.3. So P to the X is 0.3 raised to the 2. And then it's multiplied by 1 minus P, so that's 1 minus 0.3 is 0.7, raised to N minus X. N is 3, X is 2, 3 minus 2 is 1. So there's nothing there, but it's implied that there's a 1 there. So if we actually just use this equation, right, we would get 0.063. So this basically, I'm showing you how to do this by hand, right? P times 1 minus P, right? That's it right there. That's it in shorthand, right? That's the total. Well, here's actually the equation that you can use. So again, I'm showing you how to do this by hand to make sense of the equation. So now we can actually start to put this together. So remember, there are 3 possible combinations, right? First person makes a purchase, second makes a purchase, the third one doesn't. And the second combination, let's say the first person makes a purchase, the second one doesn't, the third one does, and the last one, the first person doesn't make a purchase, and the second and the 3 do. So here's the outcome, and here's the probability. Notice that they're the exact same, right? 0.063 in every case. That makes sense because remember, with combinations, order does not matter, right? It doesn't matter in which order the success and failures happen. So we've now learned that there's 3 combinations, 3 possible combinations for what we're interested in, right? 2 successes out of 3 trials. And here's the probability of each one. So we can put these 2 together. We can put, right, and remember we've been looking at for the random variable X, the outcome if 2 out of 3 people make a purchase, right? We can put this together. So here's the combinations, right? We've already calculated this. This is equal to 3, right? We've calculated that there are 3 possible combinations, right? And then here's the probability of those, right? We already calculated that, 0.3 raised to the second, right? And 0.7 raised to 1, right? If we multiply those numbers together, we get 0.189, which if you remember from the beginning of the video I showed you, right? The answer should be 0.189. So we've actually just solved this. We've actually figured out what is the probability that 2 of the 3 people make a purchase, right? It's almost 19%, 0.189. So let's just take a step back and think about this conceptually, what we just did, because I know I threw a lot at you. Basically, right, we're interested, right, in calculating the probability of an event, right? We want to know, hey, what are the chances that if 3 people come into the store, 2 of them make a purchase? Right, that's an event. But before we can calculate the probability of an event, we need the probability distribution. So that's what we have to create, and that's actually what we created. We only created part of it. We created this part right here. So in order to create the probability distribution, what we did was we said, hey, we have to figure out what are the possible combinations, how many of them are there, what's the probability of each, and multiply those together to find out what's the total probability. So basically what this is this right here, this is our random variable x, right? The number of people that are going to make a purchase in the store. The outcomes, the possible values for that random variable x are 0, 1, 2, and 3, right? No one could make a purchase. One person could make a purchase. 2 could make a purchase, or all 3 could make a purchase, right? And then here are their respective probabilities, right? So it looks like it's most likely that only one person will make a purchase, and it's least likely that 3 people would make a purchase. So we've calculated the probability distribution. We only calculated it for here, but we could go back and we could calculate what is the probability that 1 of the 3 make a purchase, right? We'd do the same thing where we'd go through and we'd calculate the possible combinations, and then we'd multiply it by their respective probabilities to get the total probability. So that's what we did. So remember in the beginning of the video I showed you the binomial probability function, right? Does that now look familiar? Right, it's the combination, right, nx, right here, which is what we calculated, times by, right here, the probability of the successes, which, remember, is back here, right, the probability of a particular sequence of trial outcomes. Right, and we multiplied those numbers together, right, and that's what is our probability function. So if that's a formula that I showed you in the beginning, well, I just showed you where that comes from, right? So for each of the possible values of your random variable x, if you took the combinations, the number of whatever the value is that you're interested in, multiplied it by the probability of that combination, you would get the probability, right, which is what we did here. We took the combination times by the probability to get the total probability, right? And we should do that for each of the possible outcomes of our random variable x, right? And that would give us our probability distribution. So I showed you that. So it's good to understand conceptually where these equations come from. So basically that's the purpose of the video so far. But now that I've showed you that, I've made you, learn how to do that by hand. There's actually a shortcut in Excel using the binomial distribution function. So let's actually solve this problem in Excel, and you're going to cry at how easy this is after I just made you do all that advanced math right there, right? So the function is equal binom dot distribution, and it takes 1, 2, 3, 4 arguments. So x, right, we already know that. That's the number of successes, n is the number of trials, p is the probability of success, and then for cumulative we're going to write false. We'll learn about what cumulative means at a later chapter, I think in the continuous random variable chapter. What that means. We'll come back to that. So just trust me for right now that you write false for that. So if this is our function, right, we would plug in for our variables our examples. So let's go to Excel and do this. So remember, I've already shown you here here is the answer. 0.189 is our example. So let's do this together. So we type in binom.distribution, open parentheses, and Excel starts to tell you what arguments it takes. So number S, right, that's the number of successes. So how many successes are there? 2. The next one is trials. How many trials were there? There were 3. What was the probability of success? Right, it was 0.3. And then remember, the last one is cumulative. Just trust me and write false and hit enter. And then we get 0.189, which is our answer. So you can, if you want, when given an answer, you can use this binomial probability function to calculate each probability for each of the values of the random variable x. or you can just use this shortcut. But like I said, it's always important to understand, when you're given these equations, where do they come from? What do they mean, right? They actually come from something that's pretty logical. So I like to show that to you so you appreciate and understand the basics of it, because otherwise you're just plugging in values mindlessly and you can't appreciate where they come from. So I hope that video made sense. The next video I'm going to show you how to calculate the mean, standard deviation, and variance for a binomial distribution.